So I'm just going to have a look at question 7. This was one of the homework questions. We've got these 4 vectors, v1, v2, v3 and v4. And we want to investigate all the possible linear dependence relations among these 4 vectors. Let's just make sure I answer the question. Let's just, the first thing it asks is, why must this subset of R3 be linearly dependent? Right, now of course we're going to go on and find the linear dependence relations, so that in itself will prove that they must be linearly dependent. But it's really looking for a reason that we could tell in advance that this had to be the case, that they have to be x1, x2, x3, x4, not all 0, such that this linear combination of those vectors adds up to 0. Why must these 4 vectors in R3 be linearly dependent? Well, because there are 4 of them, right? 4 is too much, that's greater than the dimension of the space that they lie in, so they must be linearly dependent because 4 is greater than 3, which is the dimension of R3. Now I think at the point at which this homework was set, we hadn't actually done that proposition, but I think it's something that you'd seen before in MAH00003. Perhaps you might have just remembered that. Anyway, it's not a big deal. Let's go ahead and try to find all the linear dependence relations between these vectors. So we're looking for all possible real numbers x1, x2, x3, x4. Such that this linear combination of these 4 vectors is the 0 vector, 0, 0, 0. And you probably noticed this amounts to a set of 3 linear equations in these unknowns x1, x2, x3, x4. So if you look at the top row says x1 plus 2x2 plus x3 plus x4 equals 0. The second row says x1 plus x2 plus x3 plus 2x4 equals 0. And the third row says 2x1 plus x2 plus x3 plus 3x4 equals 0. Right, so it's a set of 3 linear equations, homogeneous linear equations in the 4 unknowns, x1, x2, x3, x4. And this is the coefficient matrix of that system of linear equations. Right? This is equivalent to that matrix times the column vector x1, x2, x3, x4, coming out to the 0 vector of length 3. Yes, if you multiply this out, then the x1 hits the first column, which is v1, the x2 hits the second column, which is v2, and so on. So you get precisely this linear combination of the columns of this matrix, which by design are these 4 vectors, v1 up to v4. Okay, so the next step is the standard algorithm for solving a set of linear equations by row reduction. And what you do, and what I think all the people that attempted this question pretty much did this, knew what to do with it, or got the right matrix and knew what to do with it. So you reduce this by row reduction by a series of elementary row operations, which I won't spell out in detail because I think you all know how to do this, but after a sequence of elementary row operations, we can turn this into the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, minus 1, 2. So this is a row equivalent matrix, but it's in reduced row echelon form. So we've got these leading ones, these pivots, in the first 3 columns, and notice they have zeros both below and above those leading ones in those columns. And these mark the dependent variables, x1, x2 and x3. And the other column corresponds to the independent variable x4. Now the point is, the important point is, these two matrices have the same null space, right? Any x1, x2, x3 and x4 satisfying the system of linear equations corresponding to these rows of coefficients. It's the same as those satisfying the linear equations corresponding to these rows of coefficients, right? They're equivalent systems of linear equations, but these ones are very much easier to solve. When we look at the, x1 plus x4 equals 0, or x2 minus x4 equals 0, or x3 plus 2x4 equals 0, we can read off an expression for each of these variables, each of these dependent variables, x1, x2 and x3, in terms of the independent variable x4. So, so what we find is that the solution is that, so we get, we get x1, x2, x3, x4 equals, well, x4 is just anything, but in terms of x4, we read off what the others must be. x1 is minus x4, x2 is x4, and x3 is minus 2x4. So that's x4, which I could have called lambda or something, times the vector with a 1 in the fourth position, and in the other three positions corresponding to the dependent variables we get the entries minus 1, 1, minus 2. And you can see how they came out to be minus the numbers that we see in this column are in these positions here. So the conclusion is that the null space of A is equal to the span of this vector. Okay. So all possible multiples of minus 1, 1, minus 2, 1. Now, so far so good. I think where some people fell down here was on the interpretation of what this means for linear dependence relations. The original question was to find all possible x1, x2, x3 and x4 that we can put in here to make a linear dependence relation. And what we found is that up to a scalar multiple, it's all these linear dependence relations are all multiples of this one. So let's put in, so x1 is minus 1, x2 is 1, x3 is minus 2, and x4 is 1. Right, so here is a linear dependence relation that we've found between these four vectors. Now, we can check this, right? We've got the four vectors sat in front of us. We can check this works. Does it really work if we actually work out minus v1 plus v2 minus 2v3 plus v4? We can check that it really does add up to 0. Let me just look at the first entry. So we get minus 1 plus 2. That's plus 1 so far. Then minus 2, that's minus 1 so far. And then plus 1 is 0. And the same, all three entries will work like that. And what we found is that the linear dependence relations are either this one or scalar multiples of this one. Right? That's the only possibilities. That's the only x1, x2, x3 and x4 that will work. Okay. So yeah, I mean, for a written solution I should write down the linear dependence relations, all the multiples of this one. I'll just say it verbally now. But now there's this part of the question coming next. hence express each VI as a linear combination of the others. Now, the first time I set this question, many people forgot to do that bit, they overlooked that bit. So I put in this bit in brackets saying, don't forget this bit, exclamation mark. So what happens, you know, lots and lots of people forget to do that bit. I assume they must have forgotten to do that bit because, I mean, this is a very clear question, right? I mean, hence express each VI. So each VI, what does that mean? Well, that means V1, V2, V3 and V4. For each of those, express it as a linear combination of the others, right? So that's a completely clear, straightforward question in plain English telling you precisely what to do. So let's express V1 as a linear combination of the others. Well, we've got this linear dependence relation. How do you rearrange that to express V1 as a linear combination of the others? Well, of course, you just do it like this. V1 equals V2 minus 2V3 plus V4. Yeah. Now what does each mean? Each means you do it for the others as well. So V2 is going to be, we're going to have to take the others across the other side. So V1 plus 2V3 minus V4, if I'm not mistaken. V3 is going to be, so I'm going to have to take it across the other side and then divide by 2. So this will come out to minus a half V1 plus a half V2 plus a half V4. And finally V4 is there, so I'll take everything else across the other side. So V4 is going to be V1 minus V2 plus 2 V3. Yeah. So really, yeah, you could all do that, right? I mean, whether you overlooked it or misunderstood it or what, yeah, it's not an unreasonable demand, I think. Right, so now in part B, we sort of start all over again with a different set of vectors. So with a different set of vectors, so now V1 is 1, 1, 2. Oh, hang on, they're looking pretty similar. V2 is 2, 1, 1. V3 is 1, 1, 1. The only difference is V4, which is now, instead of 1, 2, 3, it's 2, 2, 3. So we've just changed V4 in one entry. And it says again, find all the possible linear dependence relations among these vectors. And well, I won't go through the details, because it's just, you just do exactly the same kind of thing as before. But of course it works out a bit differently. So what we find is, well, because we just changed the last column of the matrix, and then we reduce it to reducer echelon form as before, and you get another matrix, and yeah, this time we'll find that the the solution space looks instead like this. So it will be all multiples of minus 1, 0, minus 1, 1. Now that's not, these aren't the VIs or anything. You remember what these are. This is x1, this is x2, this is x3, this is x4, where these x's are the coefficients in a linear dependence relation. And strictly speaking, I should say it's only when they're not all 0 that it is a linear dependence relation. But anyway, so they go in that position. So we're looking at all multiples, or all non-zero multiples of this vector of x's to be put in these positions. So x1 is minus 1, x2 is 0, x3 is minus 1, and x4 is 1. So there's that, you know, there's a linear dependence relation, and all the other linear dependence relations are multiples of this one. So for instance, minus 3v1 minus 3v3 plus 3v4 equals 0 is an example of another linear dependence relation between these vectors. Now the difference here is one of these x's has to be 0, x2 has to be 0, the number in front of v2 has to be 0, so it's like we've got 0 times v2, which means that we can't rearrange this to express v2 in terms of the others. To try and express v2 in terms of the others, you would have to divide by 0, and you can't do that. So it's where you've got a 0 coefficient that you can't express that one in terms of the others, but where you haven't got a 0 coefficient, then you can do it just as before. So for instance, v1 is equal to minus v3 plus v4, and v3 is equal to minus v1 plus v4, and v4 is equal to v1 plus v3. Yeah, so v1, v3 and v4 can be expressed in terms of the others, but v2 can't because it has a 0 coefficient. So remember, this is an alternative way of looking at linear dependence. A set of vectors is linearly dependent. One way of looking at it is that there's some linear dependence relation, some linear combination of those vectors, not all of whose coefficients is 0, that comes to the 0 vector. But another way of putting that is that at least one of them is expressible as a linear combination of the others. And it's wherever you've got a non-zero coefficient, then you see one of them that can be expressed as a linear combination of the others. So there's at least some of them, or at least one of them, expressible in terms of the others, but not necessarily all of them, because one of the coefficients might still be 0, even though not all of them are. Right, I think that's it.